My name is Michael Jennings. I'm a HPC sysadmin at Lawrence Berkeley National Laboratory. This talk is a little bit different from most of the talks at this conference. It's going to be geared more toward the sysadmin type, so I hope there are some of those in the audience. If you're an end user, though, I encourage you to take this information back to whoever runs your systems, because it may help enhance your user experience. So I want to start off by talking a little bit about who my group is, what we do. We started back in 2000-2001 as a group who was to provide cluster services for investigators at Berkeley Laboratory. As I'm sure you all know, Berkeley Lab is responsible for NERSC, the National Energy Research Scientific Computing Center, which is a national center that caters toward investigators all across the country throughout all of DOE and academia. And so NERSC was not permitted to show any favoritism toward Berkeley Lab researchers. And as a result, when they would get a grant or an opportunity to purchase a cluster, they didn't have anyone to run that. So my group was started in order to run those clusters for those researchers. We've evolved over time from simply running individual clusters to providing condo computing and a centralized cluster resource for all of the lab that is paid for by laboratory funds. We are also responsible for all of the high-performance computing that is done through the IST department at the University of California, Berkeley. So I actually work for UC Berkeley as well. And we did a shared UC system pilot project recently that wrapped up with us and San Diego. So our environment is fairly unique across the HPC realm. We have 2,200 nodes spread across 27 different computational clusters, and all of these are under a single umbrella. We have one master node, which also runs our scheduler and our resource manager, and that setup is responsible for not only scheduling jobs on our shared systems, but also on all of the individual PI clusters. So each cluster can have its own policies, its own users, its own everything, and all of that is managed centrally. We have lots of different file systems. Some are Linux NFS servers, we call those IO nodes. We also have NAS devices from NetApp and BlueArc and Hitachi, as well as a couple of Lustre file systems. Again, all of these are under a single central umbrella, and then each node has its own local file systems as well. And our hardware is not at all homogeneous. We have in excess of 30 different distinct types of node, all within the same infrastructure. Just to give you an idea of what we're looking at on a daily basis, this is one of our graphical dashboards that shows you all of our different systems. Each one of those little colored boxes represents a node. Anything that's light blue is idle or nearly idle, and the more red it gets, the busier it is. So as you can see, we have a reasonable number of nodes, and they're spread across a wide variety of clusters and implementations. So as we grew and grew, we started having a problem. We were having difficulty keeping up with the wide variety of systems that we had to manage and maintain, and making sure that each individual node was performing optimally. We found that the same issues were coming up over and over and over again. For example, when we get a new system, there are a series of things that we have to do to each of the nodes to make sure that it's configured appropriately to be running user jobs. Turning off hyperthreading is a big one. And if somebody happens to miss a node, or if we send a node out for repair and it comes back to us, we have to make sure that we do that. And occasionally we run across a node where that had not been done, and it was affecting user tasks. And if you have a tightly coupled application that's running across a couple hundred nodes, any one node in the picture that's not performing up to snuff is going to slow everybody down. So it's very important that each node is configured correctly. We would also have, obviously, periodic disk failures. File systems would remount themselves read-only, and user jobs would try to write to them and blow up. We have file systems when a node boots that might fail to mount, and we wouldn't catch it until a user tried to write to the file system and their job blew up. Network interfaces, same thing. They happen to not come up for whatever reason, and again, user tries to run job blows up. And then everybody's heard of the killer going off and taking out things like SSHD because a user job consumed all the memory on the node. These were all very critical occurrences that had an adverse impact on the user experience on our systems. When these things go wrong, jobs end up failing. And our job is to make sure that users can do their job, to do the science that they need to do. And if they can't do their job, they get angry. And nobody wants that. So how do we fix this problem? Well, the solution that we came up with is a feature that is common to pretty much any scheduling system or resource management system that's out there. Each one of them, in some form or fashion, offers the ability for each node to run a node health check script of some kind that can perform a series of tests to make sure that the node is configured correctly and performing correctly. And if any node fails any of these different tests, it can be taken offline so that no user jobs get scheduled to it, and then you don't end up with angry users. So when we went to implement our own instance of this node health check, we looked around to see what other sites were doing. And we quickly realized that everybody was doing their own thing. Everybody had a one-off custom script that somebody, either they themselves had written, or somebody who used to work there had written, or somebody that they didn't even know, never heard of, had written this thing. They didn't really understand it. It just kind of worked, and it was what it was. But there wasn't really any sort of central effort to do something intelligent around making sure that our compute nodes work the way they're supposed to. And worse than that, all of these homegrown custom scripts were basically little shell scripts that ran through and did a bunch of things without a whole lot of thought to how the job was being done. And any of the larger centers will tell you, if you have a tightly coupled job and you're sitting there running random shell scripts that are doing 50 or 100 different execs out to sed and grep and awk and all these other commands, there's a lot of OS noise that generates, and it can really impact a tightly coupled job. So that we perceived a need for two things. One, we needed a framework for creating these checks and running these checks in a way that was clean and efficient and as unimpactful as possible to the user jobs on the node. Ultimately, we have to make sure that the science is getting done. That's our job. And so we want to interfere as little as possible with the science that's being done on each of these nodes. And so it's worth our time investment to actually take the time and write something that's done well and is efficient and is robust. But a framework is a nice idea, something conceptual, but we also needed an implementation that we could actually institute on our nodes to solve these specific problems that we had run across. Adobe is telling me it wants to update. Thanks, Adobe. Okay, so our solution was to write our own Node Health Check script and framework in a way that would be useful and portable to not just our site, but any other site out there. We wanted something that users could take and download and get up and working on their own systems quickly and easily, but also something that made it simple and straightforward for other users at other sites to contribute back their own checks. Obviously, we don't have all of the different types of equipment that are out there, and so there are other sites that are going to have to be able to contribute their own solutions to their own specific problems above and beyond what we ourselves have experienced. And the goal was to create kind of a community effort around doing this problem, solving this problem in the right way, the best possible way. So we came up with a modular design that offers dynamic loading and execution of arbitrary sets of checks. It's real easy to create your own checks and to integrate them into the script just by dropping a single file or a few files into a directory. And they get automatically loaded and parsed, and then you can use those checks in your health check script. It's all done in Bash, so you've got shell variables to customize your configuration, and your checks are just shell functions. There's a single configuration file that works across all of your nodes. We wanted to be able to have one single central point of administration for this. We didn't want to have to go to each individual node or each individual cluster and write a separate config file for each one. That didn't make any sense. We centrally manage all of these clusters under one umbrella, so we wanted to do the same thing with the health check. One config file across all nodes, no matter what the hardware is. One file. That's it. And we also wanted to provide a feature-rich implementation because all sites are different. Everybody has different needs, and we wanted to be able to hit as many of those different types of need as possible. Some sites want to be very, very thorough and do very deep and involved checks to make darn sure that their nodes are exactly the way they should be. Other sites are very, very concerned about OS noise and want to minimize to the greatest extent possible any sorts of checks that they're doing. And so we needed to provide the feature set that would enable both of those diametrically opposed possibilities. One of the things we came up with was Detached Mode, which I'll talk about a little bit later, but that's a unique feature for us. We integrate with Torque, Moab, Slurm, PBS Pro. We have support for Univa Grid Engine and initial support for IBM Platform LSF. So far, I don't know of anyone with an LSF system who's using it, but the basic hooks are there, and we would welcome any LSF users who want to test it and give us feedback. We've got checks already built into it for a number of different features out of the box, and one of the things that I, as a software engineer, not just a systems engineer, like, we actually unit test all of our different checks. So if we make changes to a check, we have unit tests to make sure that none of those changes have broken any of the checks that we've already written. This is a list of the key features that we offer. I won't go through every single one, but as I said, we're 100% native Bash. Anything Bash 2.0 or higher should work. So RHEL 4, RHEL 5, RHEL 6, any of the more recent Fedoras. I don't know how far back we go on SUSE or Debian, but anything Bash 2 or higher should work. You can match the nodes in your cluster based on glob expressions like star.foo, or regular expressions, or even node ranges. If you're familiar with PDish or similar tools, we support node ranges as well. You can run under a resource manager, you can run under a scheduler, you can run under cron, or all of the above. It's configurable via the command line and or the config file. Let's see. We have a built-in watchdog timer. One of the things when we first started writing this that was important was running under Torque. We use primarily Torque at our site at this point. And Torque, when it runs the Node Health Check, it's single-threaded, which means the PBS mom process will actually block until the health check script returns. So if you've got a health check script that's going out and running a bunch of DF, and you've got an NFS problem or a network problem, that command is going to hang, which means your health check is going to hang, which means your PBS mom is going to hang, which means your user job is going to be in a world of hurt. So we wanted to make sure that we avoid that problem in two ways. We do as little as possible in terms of forking and running subcommands. Almost everything we do is in native Bash. We do file I/O in native Bash. We do array processing in native Bash. We spawn as few commands as absolutely necessary to do the job. And we have a built-in watchdog timer, which executes and sleeps and waits for a certain amount of time, and if the health check script is not done by the end of that time, it kills it. So you don't have to worry about your health check script going off into La La Land and hanging up your resource manager. We have 30 checks currently built in, and we're always working on more. We also welcome contributions from the community, since the whole community thing is kind of the point. We have had checks contributed by the community, and we've also had ideas contributed by the community, where someone says, I would like a check that does this, and then I or someone else will go off and write it. So we're open to that as well. So I wanted to go over the configuration file syntax really quickly. It's pretty simple. You just have your host mask, which is your glob expression or your regular expression or your node range, a double pipe. That's not an OR, it's just the delimiter that we use, and then stuff. And that stuff can be anything that's valid Bash syntax. You can set shell variables in your config file, you can run subcommands in your config file, or you can do your checks. All of the checks that we ship with NHC are shell functions, but that's not a requirement. It can be anything you want it to be. I have some examples up there of the different glob and regular expression and range syntax. And you can even do more complicated shell syntax stuff if you so choose. So as I said, we have 30 checks that are already built into it. We have checks for DMI for your hardware information. It'll actually run the DMI command and read in all of the information and parse it into a data structure so that you can look up information by handle and type if you want. So you can specifically narrow down exactly what string you're looking for and match it against, for example, BIOS version or a particular memory bus speed. So you can make sure all of your nodes are running the hardware that they should at the speed that they should. There's also a raw version if you just want to do essentially a grep. We can look at the contents of files. We had some instances where a configuration file was changing unbeknownst to us, and we weren't sure how it was happening or why, but we wanted to make sure it didn't. So we put in checks for particular regular expressions within the configuration file so we can verify that the configuration is what it should be. We also have file system checks. You can look to make sure that each of your file systems are mounted. You can make sure they're mounted read-write or read-only, whichever the case may be. And if you have a file system like /temp that's on a local disk and it goes from read-write over to read-only because there's an error, it will get flagged. You can look at file system size in terms of total size or used space or free space. Those work on absolute values like some number of megabytes or some number of gigabytes, or percentages. Either one is valid. We can also check inodes. We have some customers in the genomics fields that will have millions upon millions of small files, on the order of hundreds of millions of small files on a single file system. And if you have that situation, you're quite familiar with the possibility of running out of inodes. So this allows us to take nodes offline and send out alerts if we start to run low on inodes on a particular file system. One other thing that's fairly unique to us is support for NVIDIA HealthMon. If you have NVIDIA Kepler Tesla GPUs, we actually worked with the guys over at NVIDIA to provide support for their new HealthMon utility, which goes through and essentially does the same kind of thing that NHC does for nodes for your GPUs. It checks different aspects of GPU health and will return back either yes, it's doing fine, or no, there's a problem. Right now it's an either or. In the future we're hoping to work further with them to flesh out the stuff that we can do, the interaction we can do with HealthMon. If you have GPUs and you want to use this, you just have to download the TDK off of their website. We have a number of different hardware checks we offer. The basic CPU info allows you to check the number of sockets, the number of cores, and the number of threads on your system. We check Ethernet devices, MirrorNet devices, InfiniBand devices. You can look at total memory, physical memory, and or swap space. And we also can look at MCE log, looking for machine check exceptions. Let's see, how am I doing on time? Okay. We also offer process checks. a lot of times if you don't turn off overcommit in your VM, you can run out of memory and the killer will come along and start killing off your processes. One that we lost several times that was especially painful was SSHD. So the original version of NHC allowed us to flag any node where SSHD or PBS-MOM or any of the other critical system daemons went missing. So check PS daemon is a positive check, meaning that you're looking for something that should be running. We also have check PS blacklist, which makes sure that something that shouldn't be running isn't running. And one that's especially useful, that's brand new, we offer a check that's service-oriented. So not only can you make sure that SSHD is running, but if it's not running, you can now restart it or recycle it. You can look for services based on various regular expressions and a number of different things. The version that has that feature hasn't even been released yet, so you have to get it out of Subversion, but it was something that was requested by NERSC and is coming in very handy. I mentioned Detached Mode earlier. Basically what Detached Mode does is it forks off a background process of itself, and the foreground process returns immediately. So if you need to run some checks that are a little bit more intensive or may result in a hang like DF, you can fork them off into the background, and then the foreground process looks at whatever happened the last time around and returns that result. So I have some example configurations here. I'm not going to go through them line by line. If you're interested, copies of the slides will be available and you can go through and look through them. But some of the examples that I mentioned about looking at configuration files, content are up there, as well as BIOS versions, things like that. There's an example of how you can check and make sure that an NFS file system is mounted NFS v3 as opposed to v4. And of course you can do it the other way around if you require NFS v4. Let's see, more examples of different configurations of CPU, different configurations of memory, and different network interfaces. I mentioned checking to make sure that something isn't running. This here allows us to make sure that no SSHD processes owned by users happen to be running, because we don't want our users randomly SSHing into nodes and running things they shouldn't be. And then here we check to make sure that SSHD owned by root is running. We also have the ability to make sure that unauthorized user processes, no users who aren't supposed to be on the node are on the node. And we can also check and make sure that all user processes are descended from whatever the resource manager daemon is, what PBS-MOM or slurm step D or whatever it happens to be. So if you're interested in downloading and using our Node Health Check tool, it's literally as easy as 1, 2, 3, 4. You just download it from the website, you install the RPM, you tweak the default config file, and you integrate it with whatever launching mechanism you choose, whether it's cron or slurm or torque or whatever. And I have a little walkthrough in the slides that shows exactly step by step how to do it at each point. This assumes you're on a RHEL 6 or Scientific Linux 6 or CentOS 6 type system. The steps are essentially the same otherwise. And it's pretty straightforward. If you're interested in more information, there are email addresses up here. You can contact us. The URL for both the Warewulf project and Node Health Check in particular are here. I did a talk at MoabCon last year where I actually went through a live demo of writing a brand new check that had never been done before in front of everybody during my talk. So if you're interested in writing your own checks or learning how to do checks that integrate into NHC, I recommend watching that video because I do it live for everybody. And with that, are there any questions? Yes. Well, not exactly. The Node Health Check runs on all of the compute nodes. It's not a job-oriented tool. It's a system-oriented tool. So the scheduler or the resource manager actually launches it across the entire system. And then if any of the nodes happen to be bad, they're taken out of circulation so that when a job does come along and needs those resources, it doesn't end up somewhere where it's going to fail. So it runs everywhere. Yes? The question was, if a job is running and a node fails partway through, what happens? Right now, the node is taken offline by NHC. It's marked as offline, but the job continues to run to the best of its ability. Now, depending on how bad the failure is, it may complete, it may not. But at least the node is marked offline so that future jobs can't run there. There's nothing that NHC does to directly affect how that job is affected by the failure. It just flags the failure for future reference. Now that may change in the future. Schedulers and resource managers are doing more and more things with resiliency, with jobs being able to request replacement resources for things that fail. So the future, that may change dramatically, but for right now, it's a notification, and that's it.